Hello and welcome to this NASA Google Plus Hangout for the agency's James Webb Space Telescope. I'm J.D. Harrington, Public Affairs Officer for NASA's Astrophysics Division and the Science Mission Director at NASA headquarters in Washington, D.C. We have 5 panelists joining us today. Actually, they're engineers, scientists, and folks that will discuss the program status, how the tennis court-sized spacecraft will work, explain its science objectives after launch, and basically just highlight how it will impact the world, just like its predecessor, the Hubble Space Telescope. You can also ask questions right here on Google Plus and via Twitter using #AskNASA. Let's introduce the panelists we have. First, Geoff Yoder, the Program Director at NASA headquarters in Washington, D.C. Next, we have Eric Smith, the Deputy Program Director and also Program Scientist, also at NASA headquarters here in D.C. John Mather, the JWST Project Scientist at NASA Goddard Space Flight Center at Greenbelt, Maryland. Amber Straughn, she's an astrophysicist and Deputy Project Scientist for Communications and Outreach at NASA Goddard Space Flight Center. That's also at Greenbelt. And we also have John Ehrenberg, Chief Engineer at Northrop Grumman Aerospace Systems in Redondo Beach, California. And with that, I'd like to start off the panelists here to give them a chance to discuss their perspectives on the web. We'll start with Geoff Yoder. Geoff?
Thanks, JD. I want to thank everybody for participating in the first of what I hope to be many JWST Google Hangouts. This one is more focused on the overarching overview. Future Hangouts, I think, will focus on different aspects of JWST. For me, it's really exciting as the program director to lead such an exciting mission as JWST that includes our partners, our international partners, European Space Agency and the Canadian Space Agency. And through telescopes such as Hubble and other great observatories that we explore far reaches of the universe. And so each generation of NASA endeavors stands on the shoulders of previously accomplishments in order that new missions can carry out the imaginations even further into space or new regions of scientific understanding. So it's a result of our missions challenge us to think differently about space life and humanity, and gives us answers to questions we haven't even thought about asking yet. Over the next several years, NASA and its team of industry partners will complete the assembly of the James Webb Space Telescope. This bold, technically challenging undertaking involves more than 1,200 skilled scientists, engineers, and technicians from across the U.S. and around the world, which possesses a unique and interesting perspective of the mission. Their work is producing NASA's next great engine for exploration and for exploring challenging future scientists to develop new questions. Stories are often as compelling as the scientific undertaking itself. Today, JWST, and since the replan, is on track technically, budget, and schedule for our October 2018 launch. From a schedule standpoint, we currently are maintaining 14 months of funded critical path schedule reserve. And from a little bit of perspective, after our replan in 2011, we have 13 months of funded critical path schedule reserve. So today at 14 months, and we're working hard to maintain, working hard with all aspects of the program to maintain and to meet our commitments. So again, as program director, I'm extremely honored to be part of such an exciting mission, and a mission that is on track technically from the schedule and cost standpoint. And Dr. Smith and Dr. Mather will also provide more details on this exciting aspect. So I'd like to turn it over to Dr. Mather to share more of the, I think, tremendous scientific aspects of this program. Dr. Mather?
Yes, hi. I wanted to describe for you the main scientific motivations for this new telescope. When we built the Hubble Space Telescope and we got it up and working and then repaired it, we found that there were some pretty spectacular surprises in the universe. Number one, galaxies were not formed at all like people had predicted. In fact, we found that they were formed far earlier in time, farther away from us. so far away in time and space that we wouldn't be able to see them in their formation process, even with the Great Hubble telescope, because they're so far away, so faint, and their wavelengths are so far shifted into the infrared that we could see right away that we would need a new telescope of a different kind to be able to extend the Hubble discoveries. Then as time went along, we also discovered a few more amazing things. We discovered that there's cosmic dark energy and cosmic dark matter in great abundance out there, and great mysteries to be resolved. Then even after that, then we discovered that there are actually thousands of planets around other stars that could be studied by something called the transit technique. And a few have even had images taken by the Hubble telescope, so that we know that they're out there and they're worthy of great effort to study them, because some of them are even a little bit like Earth. So we have four major scientific areas that we think scientists will pursue with the new telescope. One is, what is the first thing that happened after the early universe? What were the first things that turned on? What are the first stars and galaxies like? Second question is, how do the galaxies like the Milky Way, where we live, grow up? Were they formed from small little things that started off separate and joined together? Or were they formed from some primordial, very large structure which nucleated the formation of a whole galaxy at once? Third question is, how are stars and planetary systems born? Right here in the Milky Way, we know that there are typically several stars born per year. And we imagine that if we could see that happening, we would learn something about the formation of our own solar system. Finally, a major area which we didn't know we could pursue in the beginning was, how does planetary systems evolve with time? How do they change? Because they clearly are not constant. So here in our own solar system, we can study the planets that we have. Even the dwarf planets, what used to be called Pluto is now Pluto, the dwarf planet. But it has many, many cousins in the outer solar system that are as large and as interesting, but haven't mostly been discovered. So studying all of the residue from the formation of our own solar system will help us learn about how the Earth was formed, how it became possible for life to exist here on Earth through the delivery of carbon and water, so that we could have life here on the surface of the Earth. Now, if we're extremely lucky, we'll be able to demonstrate that some of the planets seen around other stars are a little bit like Earth. Possibly even we would know that they have an ocean, which we would learn from discovering water vapor in their atmospheres. So these are the four primary motivations that people have for building and using the telescope. But of course, we're very interested as well in the surprises that will occur. For the Hubble Space Telescope, at least half of its great measurements have been big surprises. And for instance, discovering that there's a black hole in the middle of almost every galaxy was a big surprise, and it required the power of Hubble to do it. So this is the four areas that people expect to pursue, and many more will be tried.
All right, and with that, we're going to go to Eric Smith. Eric?
Hi, thanks, JD. Well, so John Mather just told you about some of the incredible science that we're going to do with this telescope, but perhaps the most important property of any telescope, astronomical telescope, is its ability to collect light. And in the case of Webb, it's infrared light that we want to be collecting and detecting because of the redshifted light from the early universe and the infrared light's ability to penetrate the dust clouds where stars and planets are forming within our own galaxy. So for those science goals that we've just heard about, we need a mirror in space bigger than any mirror has ever been flown before in space, larger than Hubble, and in fact so large that it's bigger than any rocket that we would use to launch it into space. So we have to build an infrared optimized telescope that's bigger than the rocket it fits into. So that means we have to have a folding or articulated telescope. Another important point about this telescope, because it's going to be looking in the infrared, is that it needs to be very cold because it's detecting heat radiation after all. So Webb, the instruments, the detecting part of Webb, will be just 40 degrees above absolute zero. And when you're that cold, the material properties, how things behave, how they bend, how they shake, how they move, changes completely from your experience. So you're going to have to build a telescope that looks like any other in a way that behaves in a very non-intuitive sense. If I could have a graphic up on the screen here to show you what the design of Webb looks like, maybe this will help to explain why it's so different from any other telescope. Now, most people, when you think of a telescope, you think of a tube, right? Astronomers looking through a tube in some fashion. And on the graphic, you can see two of the tube-type telescopes that people might be familiar with, the Hubble Space Telescope, which folks have heard of, and the Spitzer Space Telescope, which is maybe not quite as household a name, but it's an infrared telescope that NASA is using today. In many ways, Webb is the offspring of these two telescopes. It will have this much larger mirror that you see up there on the right-hand part of the picture, looking off to the right, and light will come in from the right, hit that primary mirror, bounce off the little secondary mirror sticking out on the tower, back through the cone into the science instruments behind. And that's where all the detection of the light comes, and then it is sent down to astronomers here on Earth, where they will begin the exciting task of unraveling what these signals mean. And I think what we'll do next is turn it over to Amber Straughn, and she can tell us a little bit about what they're going to be doing with those data when they come down.
Sure. Hi. So I am an astrophysicist here at NASA. My job is to study star formation in distant galaxies using mainly the Hubble Space Telescope. And so in a real sense, this telescope is the future of astronomy. We'll be able to use this telescope to answer these big science questions that Hubble just can't quite answer. So in that sense, I am a future user of this observatory. I'm really excited about the great things we're going to learn, which Dr. Mather's already talked about some. And then my other job kind of on the project is I do communications and outreach for the program. So part of my job is to get the news about the telescope out to the public and to get people excited about this awesome telescope that we're building. And that's really, that's a fun part of my job. It's easy to do because this telescope is really easy to get excited about. This is Hubble 2.0. We're building this telescope again to answer those big questions in astronomy. This will be the biggest telescope ever put into space, and we're building it to answer the biggest science questions of our day in the terms of astronomy. So lots of exciting things that we have planned. Again, the inspiration I think that we're able to gain from big, bold missions like this is a huge part of what NASA does, and we're just really excited about all the things that we have planned for this telescope, both in the scientific sense about what we'll learn, and also the engineering behind this telescope is incredible. So I believe we'll pass it on now and hear a little bit more about the engineering and some of the people behind building the telescope.
Hi, JD. Thank you very much. I hope everybody can hear me. I'm John Ehrenberg. I'm the chief engineer for Northrop Grumman, and I'm happy to be here today sharing a great program with you. It's a true challenge, the engineering job of a lifetime to build JWST. We've had many years of steady technical progress. We've recently completed all the optics for the flight optical system, the primary. Can I be heard? Primary, secondary, and tertiary mirrors are all finished and are in the process of being delivered. The structure that's going to hold the mirrors up is nearing completion. The wings that hold the deployable sections of the mirror are complete and being tested. And the spacecraft has actually begun fabrication. So we've had a lot of progress, as Geoff has said. We as engineers are looking forward to building this great observatory for the astronomers, John, Amber, Eric, and the world at large. So I look forward to your questions.
All right, thank you. Once again, if you'd like to ask a question, don't hesitate to send your question via Google+. or you can use Ask NASA, the hashtag Ask NASA on Twitter. Our first question comes from the group here wanting to know, will the Webb be able to decode the mystery behind the birth of our galaxy? And I guess that's going to go to John Mather.
How did our galaxy form? We have a theory, we have a story, which we get from computer simulations. We have mapped the early universe with the cosmic microwave background radiation. We saw that it has hot and cold spots in it, and we predict that gravitation acting on those regions will be able to pull material back from the expansion and cause it to collapse back down into objects. So prediction is that the objects that form first will be small, and that they will be continually colliding with each other and merging together to make a larger galaxy. So if this story is correct, then our Milky Way was made of thousands or tens of thousands of small objects that came together through the force of gravity. So how would we know if this is true? We can't just believe a computer simulation. We have to go look and see with the telescope as far back as we can. So we take pictures of the most distant universe, and we have already discovered that the early galaxies, the ones that we see very far away because we're looking back at time as we look far away, those galaxies are small and irregular in shape, but they formed much earlier than people had expected a few decades ago. So our job now is to observe them as close to the earliest moments of the universe as we can. That takes this giant infrared telescope because these objects are small and they're going away from us very rapidly.
All right, thanks, John. We have a question here, I guess would go toward to Eric Smith. Once we launch JWST, how long do we expect it to actually live, or how long will we be able to pull data from it? Eric, I think you're muted.
Thanks, JD. The mission has what's called a 5-year design lifetime. So that sort of dictates the type of quality parts you want to use. But we have a fuel tank on board which we use to do station keeping that will be sized for about 10 years of life. So the mission will last sometime between 5 and 10 years once it reaches its orbit and begins operating.
Okay. Next question is, I'm going to throw this to you, Amber. I'm not sure if you'll know. It might need to go to John out in California. But what's the power source for JWST once we get it up in the up in space? John, why don't you take this one?
The power source is solar power. We're electrically powered. We're very close to the sun. We're only 1 million miles away. So conventional solar power will work just fine.
Okay.
Let me make a small addition to that. We're a million miles from Earth, so we're about the same distance from the sun as the Earth is.
Okay. Let's talk a little bit about the data that we're going to pull down from JWST. Where does the data come down at? Where is it stored, and who's able to use it? Amber, why don't you take that one?
Well, once JWST is in space, it will operate in a manner similar to Hubble. So as far as who gets to use the data, every year astronomers from around the world get together and propose their best ideas and that's how we decide who gets to use Hubble and who gets to observe with Hubble. So that same method will apply for JWST. That's one of the really great things about these big NASA telescopes is, in a sense, they're open source. You know, the people with the best ideas get to use the telescopes, and then once the data is taken, the data is public. Anyone in the world can go and download Hubble data, and that will be the same with JWST.
Now, is there a reservation time where only JWST engineers or scientists can use the data? Or another way to put it is, how long before that data will be available to, say, foreign scientists?
So I think there are different proprietary times for different sorts of programs. Eric may be able to answer that a bit better.
Yeah, sure, Amber. The way that it's going to work for Webb is similar to Hubble. So there's what's called a period of exclusive use, when the data come down, those scientists who propose the idea get more or less first crack at it for about a year, a 12-month period. But what many astronomers are doing in their proposals is just waiving that proprietary period. So the actual time from when it comes down from the telescope to when the public can get it varies, but it's never more than 12 months. And foreign scientists have the same rights as U.S. scientists.
Thanks, Eric. Geoff, I know we had some initial audio problems from listening to you in your initial pitch, but here's a question for you. Are budget constraints going to delay the launch of JWST? You said you'll be launching in October 2018.
So today, and I hope you can hear me better now, today JWST is an agency priority as well as a national priority. In the President's budget that was released about a month ago, the profile that set out in our replan in 2011 is the profile that we believe we need to execute the mission on budget, on schedule, and technically correct to be able to meet these great scientific requirements. So today we're on track, budget, performance, technical, and schedule to meet our October 2018 launch.
Yeah, for some reason we're still having some audio problems with your microphone there, but we'll have somebody up to try and get that fixed. Eric, I think this is going to come to you. Can you give us a background real quick on how JWST is going to unfold after it gets to the Lagrange point?
Sure. It actually unfolds before it gets out to the Lagrange point. John Ehrenberg mentioned this. After we launch and as it's on its way out to the second Lagrange point, which is 4 times farther from the Earth than the Moon is, it actually does its deployments sort of when it's getting around the Moon. So if you wanted a more detailed description of the actual deployment timeline, I think John Ehrenberg would be the person to address that question.
Hey, John, can you add on that?
Sure, I'd be happy to. Our first deployment occurs about 2 minutes after we separate from the launcher, and that's the solar array that I was mentioning before, so that we have power to continue. And after about 3 days, the large pallets that contain the sun shield deploy. That is, they move down to their flight position, and the mini-booms that push out the sides of the sun shield deploy. The telescope comes up on its tower, and then the wings and secondary deploy. This is completed about 2 weeks after launch, allowing the telescope to cool for approximately 2 months and allow it to be able to take data. At that point, the wavefront sensing begins, and the final stage of the deployment, or the alignment of the primary mirror and secondary mirror, is undertaken, giving us an operational telescope. If people want to see a better animated view of all the details, I refer you to the deployment video that you can find on the official JWST website.
Thanks, Jonathan. I think this next question is to John Mather. Can you tell us why we didn't develop the Webb for servicing like we did originally with Hubble?
Yes, of course. That was the very first question our team had to consider, because we knew that Hubble was a successful project because of servicing. However, we were not able to find a place to put the telescope that could enable it to be cold anywhere that the astronauts could reach it. So the telescope has to be cold so that it can observe the infrared light that we've never been able to observe before. And there's no place close to Earth where we can go where we can arrange for that. So the first closest place we could go was this place we have chosen, the Sun-Earth Lagrange point, 1 million miles farther out from the Sun than we are. So 1 million miles is farther than the astronauts can go right today. So that's why it's not designed for servicing. If the technology continues to progress, then robotic servicing will probably be available, but we have not designed it to be able to use that. There are no user serviceable parts inside.
Thanks, John. Jonathan, we're going to go back to you. A lot's been said about the technological innovation that needs to go into the web. Can you explain what that means and give us an example of that?
Sure, I'd be happy to. In fact, my first job on JWST was developing one of those new technologies. Back prior to the preliminary design review, when we had to be confirmed as a mission, there were 10 identified technologies that needed to be proven to outside experts to be ready to enable us to build the web. One of those was the backplane, and I was the test conductor that ran the test. We took a sixth of the backplane and put it into a test chamber and showed that it would perform, deforming only a few nanometers per Kelvin and meeting our requirements. So we did a number of technology developments, areas in the detector, electronics, materials to build the telescope, the mirrors themselves, and that was completed about 2007. So a number of technologies were developed. Unlike previous missions, there was a large investment in this program up front.
Thanks, Jonathan. Next question is, once the Webb is in orbit, what propulsion systems will be used to maneuver the spacecraft to actually look at objects in space? Eric, we're going to send this one to you.
Okay. When the Webb is on orbit out at L2, it doesn't actually sit there, it orbits the point, it will use reaction wheels and gyroscopes, just like the Hubble Space Telescope does, to control its pointing. And over time, it will use that fuel that I mentioned earlier to do what is called station keeping, to keep it in this orbit around L2. But it will have these spinning flywheels, you can think of them that way, 6 of those, and as you move and change their rates of speed, the telescope reacts opposite to that, the equal and opposite force, and so that's how you point and control it. Once the telescope is looking at a particular target, then we use an instrument called a fine guidance sensor, which was given to us by the Canadian Space Agency, and it will lock JWST or Webb onto a particular star, and then these reaction wheels will keep that star steady, allowing the other science instruments to collect their data.
I see. This question is going to be targeted toward John Mather. How will other telescopes on Earth, those like on Mauna Kea, overlap the capabilities of the James Webb Space Telescope?
Well, we've designed our observatory to be complementary to everything that we knew that could be accomplished on the ground. There's no point in putting a great effort to put a telescope in space if somebody could do it as well or better on the ground, because it's always cheaper to do it on the ground if you can. So our telescope, the James Webb Telescope, is built to observe at infrared wavelengths that really can't be seen from the ground, because the telescope on the ground will glow and emit its own infrared light, or because the atmosphere is opaque and stops the light from coming in. So for both reasons, we've designed our observatory to do those particular features that are difficult from the ground. On the other hand, some things can be done on the ground, as the Great Keck Telescope has been complementary to the Hubble Space Telescope, and discoveries with each one can be followed up with the other one. So we expect similar features in the future. As you know, we're building and hoping to build some very, very much larger telescopes on the ground, maybe 20, 30, 40 meters in size. And some of them are in progress already. That's to say 60, 80, 100 feet across. So much larger than the James Webb Telescope even. As those telescopes are built and come online, we certainly expect them to be used to follow up the discoveries that are made with the James Webb Telescope.
All right, thanks, John. Amber, we're going to send this question to you. Will there be any real-time image website capabilities with the James Webb once it's up?
Any real-time imaging capabilities? Well, again, the way we will use this telescope will be by selecting proposals that were written in advance to look at the most cool things in the universe. So it really will be by a detailed process in order to pick out the right things to observe with this telescope. So in terms of real time, there won't be quite as much of that, but as soon as these big discoveries are made with Webb, which we know will happen, we will have a similar process of press releases, and we'll be active on social media. So all of these things, as soon as those results start to come out, then we will definitely get them out to the public.
Thanks, Amber. One of the questions we have, I'm going to send this to Eric, is how big are the mirrors going to be on the James Webb Space Telescope? I know that they're going to be pretty large, and the tolerances to be able to fold them and get them into the rocket that's going to launch it into space is really tight. Can you give us a brief description of that?
Sure. The diameter, if you will, of course it's a hexagon, but the diameter of the primary mirror is 21.5 feet, 6.5 meters. Hubble is 2.4 meters, just for a sense of comparison. It's made up of 18 hexagonal segments. Each of those segments themselves are just a little under 2 meters in size. And of course, you want your mirror to be nice and smooth across its surface to give you those good sharp images. And if you were to take the telescope mirror for James Webb Space Telescope, make it as big as the United States, so sort of, imagine the mirror that large, and the biggest ripples you would have in that sort of the mountains in the country made up of the James Webb Space Telescope primary mirror would be less than 3 inches tall. So that gives you some indication of how flat the mirrors are, and it's, like I say, 21.5 feet across.
Thanks, Eric. Jonathan, can you tell us a little bit, going back to these tolerances and that, when you're talking about such tight tolerances to get the actual telescope into the rocket, won't you have problems with vibration when the rocket is actually launching off the launch pad and that?
Let's see. Vibration is a normal problem that we have to deal with in designing satellites. All of the mirrors are restrained for launch, so-called in a snubbed position. I alluded to technology development. One of the early technology developments that was related to the mirrors was proving that our mirror design would survive just such launch vibrations. So we took a mirror blank early in the program and subjected it to launch vibrations and proved that it maintained its shape. So yes, that is a serious concern. It was addressed very early, and that risk was retired about 5 years ago.
And actually, JD, if I could add something I've seen, and I think that may be visible on the JWST website, there might be some little videos of one of those mirror segments undergoing that violent shaking. And I can tell you as an astronomer, it's absolutely frightening to see that thing shake like that, but it's gratifying to see it survive.
Thanks, Eric. Let's go to the next question here. And once again, if you'd like to ask a question, you can do so right here on Google+, or you can send a question via Twitter to the hashtag AskNASA. Well, the question is, how will JWST observations help to better understand black holes? John Mather, we're going to go to you with this one.
Okay, well, James Webb Telescope will be observing the history of black hole formation by observing early galaxies to see where the black holes occur first. So the way, of course, that we observe black holes is by watching things fall in. A black hole, by definition, is something where nothing can come out. So what it does is it has extremely strong gravity, and if a piece of material, a gaseous cloud or a star or a planet, were to fall in, it would be compressed to a very high density and raised to a very high temperature and capable of transmitting very large amounts of power, either X-rays or radio or infrared, so that we can see them. So that's our job, is to see the history of that happening. The big question for astronomers is, which came first, the galaxy or the black hole? Now that we see them today, all the galaxies have at least one big black hole in the middle. But we don't think that the black holes started out big. They probably started out small and then somehow grew by absorbing material. So this is something to be learned by observing. We've got many stories from theoretical calculations, but very difficult to explain the actual history that we've seen.
Thanks, John. Right now, I hope we've got Geoff's microphone situation fixed, but this question goes out to you, Geoff. Why is it taking so long to build and launch the Webb? I mean, we've delayed it a couple of years ago, and now we're looking at 2018, so that's still a good 4 years away, almost 5 years. So if you could tell us that.
Yes, hopefully you can hear me better than before. As both Dr. Mather and Dr. Smith pointed out, the tremendous science benefits we will give to JWST. But to achieve those benefits took development of new technologies that we didn't have before. Things like the large mirrors that Dr. Smith talked about, areas that John Ehrenberg had briefly mentioned, things like the composite background. We're operating in temperatures we've never operated before. So we needed to develop technologies to be able to achieve this tremendous science. Once you develop the technologies, we certainly need to test the technologies, then integrate it as a system. And since we're out at L2, basically 1 million miles away, it needs to work when it gets there. So we have a robust test program to be able to fully test and exercise the observatory so that when it gets out to L2, work the first time.
All right, John. Geoff, for some reason we're not able to get your audio cleared, so we'll keep trying. Here's a great question, and I'd like to go back to Jonathan with this one if we can. Jonathan, is JWST in danger of being hit by space debris? It looks very vulnerable.
Let's see. We're not at risk for being hit by space debris. Our orbit is considerably above the typical low Earth orbit or even the geosynchronous orbit, where lots of debris from previous space flights are. But we are subject to micrometeoroids that are part of the interplanetary environment. And one of the key jobs of the engineers, like myself, and all the members of the team is to design a system that is capable of surviving in that environment. So we have, as part of, again, the technology development that we talked about earlier, subjected elements of the sun shield and the mirrors to hypervelocity impacts and included those degradations in the design. That is, the design is a little bit more robust than it would have to be in the absence of this micrometeorite environment. So the answer is we will be struck. Typically, these micrometeorites are very, very small, but they have a lot of energy, and their impacts on the system have been calculated and included in the design.
Thanks, Jonathan. I'd like to ask a question of Amber here that just came in. Who or what was the James Webb actually named after?
So James Webb was the administrator of NASA, the leader of NASA during the development of the Apollo program. So James Webb was largely responsible for helping us to get humans to walk on the moon, which is pretty great. Obviously a very worthy thing for a telescope to be named after. But in addition to that, James Webb was the first person to say that in addition to sending rockets to space, we also need to be doing science. So he was a very big advocate for science early on in the early days of NASA. So we thought that would be a really good person to name this awesome new telescope after.
Sounds good. It was a good choice as well. Here's a programming question for Eric Smith. Unfortunately, we can't get hold of Geoff right now, but it takes so long for these telescopes to go through design and development. We've been involved with this one now for quite a number of years. Is JWST successor on the drawing board right now?
Yes, in fact, the astronomical community is always thinking not only about the telescopes they have today, but the telescopes they want to have in the future. And they go through a process every 10 years where they decide as a community, how do we want to prioritize what to do next for our field? And JWST was one of those top choices in one of those surveys, and it's continuing on. And in the most recently concluded survey in 2010, they've already picked the type of mission they want to do next to follow after the Webb telescope. And this would be a telescope that focuses on the mystery of dark energy. And so while Webb is looking at particular problems with early galaxies and exoplanets, the mission that folks are thinking about coming down the line would be one that is focused on dark energy and exoplanets and surveys. So yeah, we're always thinking about what comes next.
Sounds good, Eric. Thanks. Here's a question, probably, Eric, you need to take as well. Are there any military applications for JWST?
The JWST is designed to look out into the cosmos, look for very faint signals. So this is not the type of telescope that would really see any useful military application, unless, of course, we were able to detect Klingons or Romulans approaching the solar system.
Thanks, Eric. John Mather, can you tell us about the goal of observing how planetary systems change over time? What kind of changes are you expecting to observe with JWST?
Okay, well, most planetary systems don't change very rapidly, except that the planets go around the center. So, however, when we are able to find young planetary systems in the process of formation, we expect those changes to be much more rapid. So, for instance, there's one planetary system called Beta Pictoris, where it seems that comets are falling into the central star quite frequently, because we see changes of the light coming from that star that have the traces of the heavier elements that would be in a comet. So that's one where we can see. The other thing that we can do is to look at different planetary systems and see how they appear depending on how old they are, and depending on what kind of star they're orbiting around. So far it appears that the solar system is not common in its configuration, that most of the planetary systems we've been able to find are not the same as our solar system. Now, partly that's because it's easier to find certain kinds than others, and planetary systems with large planets are clearly easier to find than those with small planets. So we study what we can find and try to make a consistent story that explains everything that we see, ranging from our ideas and our observations of young planetary systems, so planetary systems that still have a lot of dust in them left over from the first moments, to very old planetary systems that have no dust left at all. Of course, one of the reasons for studying these things this way is to see whether there are any candidates for direct observations for a future generation of telescopes. We've designed and thinking about planetary systems for a long time. Something called the Terrestrial Planet Finder was conceived well over 10 years ago as a number of different choices that could be implemented to observe Earth-like planets orbiting Sun-like stars quite directly. But it's a difficult project.
All right. Thanks, John. Jonathan, I think this question is going to you. It seems to be engineer-related. What is the maximum exposure time that JWST can observe a single target before noise becomes a problem for the detector?
Let's see. Our length is limited by how long we can point at a single object. We're capable of pointing at a single object for 10 days. That's by design. The sun shield is designed to take 10 degrees of roll as we go around the sun. The noise really is a limitation of the faintness of the target and the temperature of the telescope and the detectors. And so it's really not a length of exposure issue. It's really about a brightness and temperature issue with the system. But 10 days is the longest we can look at a single target without repointing, but the astronomers are very adept at piecing together these exposures and making many multi-million second exposures. So there really is no limit except how much of the telescope's lifetime they want to dedicate to a single target.
Thanks, Jonathan. Amber, this one's coming to you. Can you tell us how NASA goes about deciding which targets to actually target? I mean, what's the process for developing our target list, so to speak?
So,
Uh-oh. Are you muted, Amber? Lost audio here.
Amber, we're not hearing you.
Amber, we're not hearing you. Are you muted? Uh-oh. Well, we'll come back to you here in just a moment. We'll give you a chance. Eric, this question is going to come back to you then, if we can. What happens to JWST after the instruments no longer work? Will it just go in the graveyard around the sun, so to speak?
Well, NASA has to have, they're called disposal plans for anything that it puts up there. Now, of course, because Webb is a million miles away from the Earth, it's not the same type of disposal plan that you have to have for a satellite that's in near Earth orbit and would eventually come back into the atmosphere. So this will stay in a solar orbit, just like the Earth going around the sun, for hundreds and hundreds of years until some culture in the future is able to go out there and capture it and bring it back and put it in a space museum somewhere.
Sounds good. John Mather, we're going to target this question to you. As you know, the Kepler Space Telescope has been staring at a lot of stars and has been finding a lot of planet candidates. Can you tell us how JWST, once up, will determine the atmosphere for these different planets to help us determine whether there's a possibility of life on them?
Yes, sure. Well, the way that the Kepler mission discovers planets is to stare at about 100,000 stars in the constellation of Cygnus all year long. And once in a while, a planet will go between us and the star, so it'll block some starlight. The subtle thing is that some of the starlight passes through the planetary atmosphere on its way to the telescope. Now, the Kepler mission doesn't have any special ways to analyze that light that went through the atmosphere of the planet, but the James Webb Telescope does. Now, we have something called a spectrometer, so we spread the light out into a rainbow, and we're able to recognize the particular changes that are due to the molecules in the atmosphere of those planets. Now, most of the planets that are discovered by the Kepler mission are kind of far away and not very bright. So we're also very eager to see other ones that are closer up. So you might, our audience might not know that a NASA mission has been selected for further study called the TESS, T-E-S-S, and it will be looking for the brightest nearby stars that also have planets that do this transiting phenomenon. So when we know where to look and when to look, the James Webb Telescope will be able to tell the chemical constituents of those atmospheres. So that's the ideal case, is to have the nearest, brightest objects. And Webb is designed to be able to do that.
Thanks, John. Jonathan, we're going to go to you. Here's another engineering type question. How do you go about designing such a mega machine such as JWST? What are the procedures involved?
The procedures involve studying the giant problem, understanding what our customers, the end users, our astronomers want, and decomposing it into smaller problems that can be solved. This is a little bit like the answer to the problem is, how do you eat an elephant? And the answer is one bite at a time. So we divide the system into components and elements, and they go into subsystems and components and assemblies, and flowing down the requirements is one of the chief jobs of the systems engineers like myself, and then verifying that that job has been done correctly and that when the system comes back together it's going to work is basically what I do all day. So there are a number of people devoted early in the program to decomposing the problem into small, solvable, provable answers, and that they're connected in a logical fashion to give us a system that works. And then as we come back up and build it, we verify it. So we like to think of it as a V, and we're climbing up the upside of the V, proving that we've built the system that's going to work and give the astronomers the performance that we all want to deliver.
Thanks, Jonathan. One of the questions we got here that just came in, probably going to go to Eric Smith. And once again, recapping what Geoff told us at the very beginning, that we had some minor problems with audio-wise. JWST is on cost, is on budget, is on schedule. But the question is, what is the exact cost of the entire JWST program? And the question is it really worth the investment? Eric?
Okay, so the cost to build or develop Webb and launch it is $8 billion, and then there will be money used to operate it after that. And you can look that number up, and it's about $8.8 billion to build and operate Webb for 5 years. If it operates longer, it obviously costs more to operate because you're operating it longer. And so then the question comes to the worth of a mission like this. Of course, because I've devoted much of my career to working on this, I clearly believe that this is worth the investment. This is pushing humankind's knowledge of the universe. This is doing things, making ourselves better, not only as a country through the knowledge we gain, through the technology we invent to do something like this. So these kinds of investments in things that make us better as a people, I think, are definitely worth it.
Thanks, Eric. Good answer. We're going to try to go back to Amber real quick. We know that the Webb is going to be a replacement for the Hubble Space Telescope, but couldn't it also be considered a replacement for the Spitzer Space Telescope, because they have the they study the same metric electromagnetic spectrum? So
first of all, can you hear me?
I can hear you.
Very good. Okay. So, well, we say here at NASA that the James Webb Space Telescope is a successor to both Hubble and Spitzer. So the fact is that it's a successor to Hubble in the sense that, you know, we've learned so much about our universe from Hubble. Hubble's completely revolutionized our understanding of the universe in many key ways, and we expect that this big bold mission of James Webb will allow us to continue that kind of effort to really answer those big astronomy questions. So it's a successor to Hubble in that sense, and it's definitely also a successor to the Spitzer Space Telescope in the sense of the kind of light that we'll study with the James Webb Space Telescope, which is of course infrared. So in that sense, it's kind of JWST will be the best of both worlds as far as Hubble and Spitzer is concerned.
Thanks, Amber. John Mather, this question goes to you. Why are the mirrors on Webb gold-plated, and how thick is this gold plating?
The mirrors are gold-plated because we make them out of beryllium, and beryllium is not as good a reflector for infrared light as other things. So gold is the best material that we can get for covering the mirrors. It's ideal for two reasons. One is that it's the best reflector, and another one is that it doesn't tarnish or get old sitting around here on the ground for the period of time that it takes. So the way that we do it is to coat the mirrors extremely thinly with gold. The amount of gold that it takes is less than what is in a typical person's wedding ring. So it's an extremely small amount of gold. It's very, very thin. But it's just the right amount for this purpose.
Thanks, John. Jonathan, question for you. We've already covered what the lifespan of JWST will be once it's launched, but do we expect the instruments to go bad, or do we have fuel, coolant or fuels that will run out beforehand? How's it going to end its mission, so to speak?
Let's see. The entire thermal design for the observatory is passive. There are no refrigerants, there are no cryogens like there are for Spitzer, although the mid-infrared instrument is cooled by a closed-loop refrigerator. So the issue is not one of losing a cryogen and then losing thermal control. Our one main consumable is our propellant, which we need to use to manage our momentum and do station keeping. If we keep that and husband it well, we will extend our lifetime. But the instruments will not be the life-limiting element on the observatory.
All right, thanks, Jonathan. Eric, we're going to come back to you for this question. I know JWST is big and as large a project as this isn't just an American entity. What can you tell us? How many partners do we have internationally? How many corporate partners? Things like that.
Sure. Any undertaking like this in science anymore is usually always international. Most science missions here at NASA are. Webb has partnerships with the Canadian Space Agency and the European Space Agency, as well as what we call the European Consortium, countries that came together to provide the mid-infrared instrument that you just heard Jonathan Arenberg refer to. So all the countries that are in ESA, and I've lost count whether there's 21 countries in the European Space Agency right now, and then the Canadian Space Agency are partnered with us. So we have partners in virtually everybody in Europe and just across the border, and they are providing key expertise not only in the form of hardware, science instruments that they've given us, but they will be involved at the Space Telescope Science Institute afterwards with astronomers working there and operating those instruments.
Thanks, Eric. And we're coming up on the top of the hour where we're going to have to close down. I think we've got time for one more question. And John Mathers, I'm going to take this to you. Can you tell us exactly when we expect JWST to launch and where will it launch from?
We're planning on about October 2018, so about 5.5 years from today. And we're launching it from Kourou, which is in French Guiana on the equator in South America. And that's chosen because that's the launch site for the Arianespace, which is a commercial organization in Europe that builds these rockets. And the rocket is one of the contributions of the European Space Agency to this partnership. So it's a little too soon to buy your plane ticket to the launch date, but we're pretty sure that we can do it there at about that time. So thanks to the congressional approval of the budget, we're continuing at full tilt to the schedule that we've announced. So that's what our plan is. Then 6 months after it's launched, then we get to start genuine scientific observations.
Sounds good, John. Thank you very much. And unfortunately, that's going to have to do it for our time today in this Google Plus Hangout on the James Webb Space Telescope. I'd like to thank our panelists today for their time. If you'd like more information about the Webb Telescope, you can join us on the web at www.jwst.nasa.gov. For more information about all of NASA's programs and projects, visit us on the web at www.nasa.gov or on any of our many social media sites such as Flickr, Facebook, Twitter, YouTube, and of course, Google+. For that, have a great day. Thanks for joining us.